Greetings, pre-calculus students. We're going to try this again. This is lesson 9.6, the complex plane and polar form of complex numbers. I'd like you to take notes on this and do the examples that we have written down here. Now, complex numbers can be graphed in something called the complex plane. This is really just like graphing in a traditional x, y plane or Cartesian plane that we're used to. We have the real axis, as you can see, which is comparable to the x-axis, and the imaginary axis, which is really just like the y-axis. So, as we know, complex numbers are in that form a plus bi. They're simply graphed as the ordered pair AB. We sometimes call the r value the absolute value of the complex number. It's really the same thing. So for instance, as you see this point graph below, negative 6, 6, that has an absolute value, kind of like the hypotenuse there, of the square root of 72, or 6 times the square root of 2. So the polar form for that point would be r theta. The r value, which we just calculated, was 6 times the square root of 2, and theta is 135 degrees because we take it to the second quadrant like that. Now, here's the meat and potatoes of this lesson. We'd like to be able to plot complex numbers on that complex plane and be able to write them in polar form, except now our polar form is just a little bit different because we have to have that imaginary part in there. So that's called trigonometric form. That's a fun word to say really fast. Trigonometric. So a plus bi, we can also write that then as r, same r that we're used to, times cosine theta plus I sine theta. And rather than always write that out all the time like that, which is rather tedious, we can abbreviate it to r cis theta. The CIS stands for cosine I sine. All right, here's some examples of what's going on here. We'd like to write 3 minus 3 times the square root of I. Again, that's a complex number because we have the real part and the imaginary part. We'd like to write that in trigonometric form. So I kind of graphed it there in the grid, and look at that nice, beautiful right triangle there on the right. I labeled it. Notice I tried to draw it kind of corresponding to the quadrant it's in, which is the fourth quadrant. So we do recognize this as one of those 30-60 right triangles. We notice that the hypotenuse is 6. We remember that from our basic stuff. And thus we can write this, this coordinate. Remember, this is really just a coordinate down there in the fourth quadrant there. We can write that as 6 cosine 300 plus I times the sine of 300. I really should have had parentheses around that cosine and the I sine part. All right, here's another example. This is going vice versa here now. Now I have 2 times the cosine of 150 plus I times the sine of 150. That's in that trigonometric form or complex polar form. I'd like to now write that in rectangular form. So there's a rectangle, very mediocre as you see. Again, this appears to be one of these 30-60 right triangles. So once I draw it out like that, I can recognize that that x value right here is going to be half the hypotenuse times the square root of 3. So there's that value. And then my y value over here will be just half the hypotenuse, which is 1. So in rectangular form then, this point looks like negative square root of 3 plus 1i. Notice it's negative because 150 degrees is in that second quadrant, and so that makes the x value negative and the y value positive. Now, you can also do this conversion simply by substitution. You wouldn't really have to write out the triangle at all. So I start with that trigonometric form, and then I just simply substitute those values I know for the cosine of 150 and the sine of 150. Maybe you still have those memorized, or maybe from your circle chart. So I plop those in there, distribute my 2 to each of those, and voila, I still have that same value that I had there. Now next, I'd like you guys to see if you can try